Begin with announcements. Contest 3 is still open, and there are still currently 0 submissions from students other than the test bot that was uploaded. So just like show of hands, how many people are planning to participate in Contest 3 who are in the room right now? Okay, not very many. So yeah, just as a reminder, it's extra credit points to what, the top 10, Davis, or something like that? Yeah, so, you know, currently you can submit a totally brainless bot that does nothing at all and gets 0 points and receive extra credit in this class, and you would be foolish not to take advantage of that opportunity. So, yeah, question?
Still not due till
Sunday? Saturday, yeah. Because we're going to need time to run all the contests to give you results by Monday. So, yeah, Saturday night. So, yeah, please do the contest. It's more fun for us than the last lecture if lots of people have done it, and getting a better grade is more fun for you. The only other thing is we do have the final exam coming up. Remember, that's going to be next Friday. We know some of you, Thursday, next Thursday. We know there were a couple of people who had conflicts with that. We should be able to accommodate people in the same way we did for the midterm, but please let us know as soon as possible if you have final conflicts so that we can schedule everything accordingly. Other admin questions? Okay, great. So today's lecture is going to be on kind of optimization in general, and then optimization specifically is applied to machine learning. This is actually a relatively short lecture, so we're then going to have some leftover time at the end, which I want to spend talking about a sort of specific, fun, probabilistic modeling problem that I worked on with one of my colleagues a couple of years ago that really ties together a bunch of the stuff that we've done in this class with probabilistic inference and with optimization and with machine learning. And so we'll hopefully have a chance to spend some time on that and look at some cool demos. So with that, let us begin. So the problem that we're focused on in today's lecture is the problem of optimization. And generically in optimization, we're given some kind of function we're going to call f of x here, and we want to find an input x to this function that's going to make f of x as small as possible. Why do we say as small as possible? This is mostly a kind of convention in the field in optimization that we always want to think of these problems as minimization problems, and we just sort of choose minimization rather than maximization arbitrarily so that it will always be clear what we're talking about. So yeah, we're talking about minimization, and when we have things that actually look like maximization problems, like the maximum likelihood objective, we're just going to put a negative sign in front of it so that everything looks like minimization there. And so remember that x in general might be sort of some kind of complicated thing. It might be some discrete valued object. It might be a big vector. But the quantity that we're trying to minimize is going to be some scalar function of x. We have seen previously in this class examples of optimization problems. And the main optimization problem that we've seen already, if you remember way back to the beginning of class when Davis was lecturing, was we looked at constraint satisfaction problems. And so if you remember, in a constraint satisfaction problem, we have some kind of discrete, we have a set of variables. Each of those variables can take on one of a discrete set of values. And our ultimate goal is to find an assignment of values to those variables that satisfies all of some set of constraints that have been introduced. And so we saw this specifically in the context of like graph coloring problems, and you had a final exam problem involving people who were trying to order food together. And why is it a reasonable thing to think of this as an optimization problem? Well, we saw that one of the procedures that we can use for solving CSPs is some kind of local search procedure, right? So if I start with some assignment of values to variables that looks like this, and I'm trying to, this is some kind of graph coloring thing where I want every node to be a different color from all of the nodes that are adjacent to it. This is not an acceptable solution to this problem, but and so we want to do some kind of local update. We're going to do some kind of local search to try to improve it. And there are, maybe we decide we want to focus on this node and we want to assign a different value to this node. There are two different ways in which we could assign a value to that node. One of them would be to turn it red like we have here, and one of them would be to turn it green like we have here. And so if we set up some kind of criterion that measures the sort of goodness or the badness of our solution, one thing that we can do is count the number of constraints that are currently being violated. And we can notice that in this case, we haven't actually made the number of violated constraints decrease by reassigning this value to the variable. And in this case, we have made the number of violated constraints decrease. So maybe this is the change right here that we want to take instead. And so the key thing to notice is that we haven't solved the problem. What we have here is still not an assignment of all values to all variables in which no constraints are violated, but we have some way of noticing that we've made some progress on the objective. So to kind of come back to the optimization language that we were setting up on this first slide, this f of x here that we're trying to minimize for the constraint satisfaction problem is one that counts the number of violated constraints. Are there other, if our goal is ultimately to produce a set of assignments of values to variables that violates no constraints, are there other optimization objectives that we could have chosen instead of this counting violated constraints? So the question is, so we said, if we want to think about this CSP thing as an optimization problem, one way we can do that is we can say this f of x here that we're trying to make as small as possible is the number of constraints that are being violated. So the question is, could we have chosen something else for f of x that would still have the property that sort of perfect solution to the CSP, one that violated no constraints, would be the minimum of f of x? Yeah? What do you mean by that?
Like earlier we were trying to, I guess that would be equivalent to violating constraints.
Yeah.
Well, I think this is pretty trivial. I'm not sure, but why not just maximize the negative? But technically that's different.
Sorry, maximize the negative of f of x. But that's the same problem, right? Yeah, so so in the back. Yeah.
If we violate 9 of them, that counts as 9.
Yeah.
What if we count how many times each constraint is violated? So if we violate a constraint more times than 4.
What does it mean to violate a constraint more times?
So I guess look at each of the, edges.
Uh-huh.
Like if it's all blue, that's 3 different edges, and that's sort of 3 violations, whereas
But each of those pairwise things is a constraint, right? Yeah.
So I guess any sort of function that preserves the order of the constraints would be like 10, 9, 8, right? We want to minimize that. So square root or like x squared or something like that.
Okay, good. Yeah, exactly. So if we're, if we have sort of number of violated, we could do, any kind of monotonic function of this, right? We could put a square root, we could square it, whatever. We could even do something like super trivial, which is to say we're going to define the function that is 1 if some constraint is violated, and 0 otherwise, right? This is a function that has the property that it is smallest when we have violated none of our constraints and larger otherwise. Question in the front?
Would any of these actually have an effective difference on the algorithm?
Okay, so this is a really good question. So let's just consider these two options here, the number of violated constraints and this 0, 1 thing. That's 1 if there's any violated constraint and 0 otherwise. What's going to happen if we come back to this slide? What's going to happen in this procedure depending on which of those two objective functions we try to optimize? Which of these is a better objective function to use?
I would say total.
Oh, yeah, sorry, somebody else.
Alright, so the number of violated constraints is better because in this case, both of the values are 1, so you don't know which one's good.
Right, so if we take this kind of like trivial objective that gives you, a penalty of 0 when you are done and a penalty of 1 everywhere else, then we can't actually distinguish between these two options here because neither of them satisfies all of the constraints. So the key thing to take away here is just that, we design optimization problems so that the solutions to those optimization problems give us the solutions that we want to the problems. But in general, there are going to be multiple different ways of doing that. and the, different things that kind of have the same minima may interact in different ways with the kinds of optimization algorithms that we try to use. And so a lot of what goes into designing optimization is thinking carefully about how to set up these objective functions so that they have the properties that we want. And we're going to see sort of concrete examples of this for machine learning applications. Questions about the kind of CSP version of this before we go on? Yeah. So we're going to say 1 if a constraint is violated, and 0 otherwise. If any constraint is violated. So this function, if we kind of imagine the space of assignments to variables, and this is just a picture, right? Like maybe these are the regions that are satisfying assignments, and everything else are non-satisfying assignments. And so this function defined over this kind of abstract space of CSP assignments is going to be 0 here, and 1 everywhere else. And we're trying to find the zeros, basically. Okay, so, and this is basically the same kind of thing that we're going to be trying to do today, but what we're going to be doing differently is we're going to be looking not at these kind of discrete constraint satisfaction sorts of things, but at continuous problems, where the thing that we're trying to optimize now is in general going to be the parameters of our model. And so to motivate this a little bit, let's just quickly recap what we know about linear classifiers and the kinds of linear models that we were looking at yesterday and last week. And so we remember the sort of decision function that we have designed for one of these models looks like this. I get an input x. I have a weight vector w for every output class that I might predict. And my prediction rule is going to say loop over all of the classes that I'm allowed to predict, take the dot product between the weight vector for that class and my input feature vector x, and then just produce the sort of identity of the class that gave me the highest score using that dot product. And this is a decision rule, and so what we then need to define is some way of figuring out how to actually acquire these weight vectors w in a way that is going to be as good as possible for our task. And we looked at a couple of different learning algorithms for doing this, both with a similar flavor. The first one we looked at was the perceptron learning rule, which looks like this, where we say when I make a prediction, and I should have predicted y star, but I actually predicted y, I'm going to sort of update the weight vector for y star positively in the same direction as x. We're going to update the weight vector for y negatively in the opposite direction from x. And this will have the consequence that the right weight vector assigns a higher score to x, the wrong weight vector assigns a lower score to x. And we saw with the perceptron update rule that it'll kind of move the scores in the right direction, but it won't necessarily fix any of our classification decisions. And so we improved on perceptron by designing this Mira update rule, which says we're not only going to take a step kind of fixed size in the direction of x, but we're actually going to choose some kind of optimal step size tau that's going to have the property that we definitely fix the particular mistake on the particular example that we were looking at right now. And we asserted but did not prove that if we run either of these learning algorithms for long enough, and it happens to be the case that there exists some separator which will perfectly classify all of the training data, then in that case this will eventually, either of these learning rules will eventually converge to some decision boundary which correctly classifies all of the data. And there are a couple of things that are not totally satisfying about this. The first of these is that we don't get any guarantees at all in the case when our data is not linearly separable by our classifier, right? So if our data looks like this, we saw examples, of ways of kind of learning wiggly decision boundaries that would maybe allow us to accommodate something like this. But assuming we're restricted to some particular class of separators, the data looks like this from the perspective of those separators, right? There's no line that we can draw through here that will perfectly classify everything, but we don't have any guarantee from using these update rules on the left that the line that we do come up with will be the line that makes the least mistakes possible, right? We don't have any promises at all. The other thing that's kind of unsatisfying about both of these update rules is that they only get to look at one example at a time. So it's possible that if I've picked up a particularly weird XY pair right now, it causes me to update my weight vectors in some direction that is not actually a good direction to move them in for the rest of the data. And all I can do, any sort of iteration of this algorithm is fix a mistake on a single training example, if even that. And it could be that the progress that we're making on the one training example that we're looking at is not actually progress on the sort of whole data set as a whole. And so what we would like is something that's going to be more robust and that's going to allow us to kind of make progress in a global sense and not just in a local one. And so the key insight here is that this is just an optimization problem of the same kind that we were looking at for CSP. So to put this in kind of the most abstract terms possible, we have some kind of model, some kind of prediction function that's going to take in an input xi and the parameters for that model, theta, and it's going to predict some kind of y. And then we're going to define some kind of loss function, some kind of measure of the progress, measure of the quality of our model. And we just want to use sort of generic tools for optimization to find a theta that minimizes this thing here. So that f of x that we were looking at on the first slide that we were trying to minimize, that's just this. And we're going to call it f of theta because we want to find the thing that minimizes the loss over my whole data set with respect to theta. So the thing to keep in mind here, right, we have sort of two things we care about. We have the training data, which takes the form of xy pairs. And we have the parameters, which we're calling theta on this slide. And when we're treating this as a minimization problem, the training data is all kind of folded into this objective, and we're only interested in it as a function of the parameters theta and not as a function of the training data itself. Questions? Yeah?
An example of what you would be putting in for data.
Okay, so if you remember, like our one class of one model we've been looking at a lot recently are linear separators. So if we just say theta is these W vectors that we've been using in our linear model, then we want to find the set of all these W vectors that minimizes the loss.
So then you would have defined that you're using linear classifiers.
Exactly, and that's all kind of like abstracted away in this function that we've called predict here. Yeah, so we could use a linear model there. We could be using a probabilistic model, something like naive Bayes or some other kind of Bayes net, and then this theta is going to be the set of CPTs associated with that Bayes net, and we might similarly want that Bayes net to give us the best predictions possible in a sense that we're about to define. Other questions? Yeah. Yeah, so remember, like we said, when we were talking about constraint satisfaction problems, we said what we really want is something that we can minimize such that when we have minimized it, it will give us the best possible solution to our CSP, right? In the case of CSP, something that violates no constraints. And so we defined what we're now going to call a loss function that measures how bad the current solution we have is. And so in the case of CSPs, we saw that it was the number of violated constraints. One sort of natural thing that we could use in the case of these linear models is to count the number of mistakes that you're making on the training set. But kind of generically, we're going to refer to this measure of our progress as a loss function. And our goal is going to be to minimize the loss. Yeah?
What exactly was yi star?
So remember, our training data looks like x1, y1, x2, y2, I guess as we've been drawing it, y star, y star. Yeah, so the correct label that should have been assigned to the ith training example. Other questions? Okay, so the only thing that we really have to answer here is how are we actually going to compute the theta that minimizes this quantity that we've drawn on this slide. And there are basically two different ways of going about this. One way of going about this is to explicitly find a closed form solution to this optimization problem you've seen before. To talk about what we mean by that, let's look at a super simple example of this. Suppose I have some quadratic that looks like this, right? Just a quadratic function. If a is positive, it's going to be something like this. It's going to be a big U shape that points up. And we want to know what x to plug into this function of x here that will make this quadratic function that we've defined over here as small as possible. We notice that this thing has a global minimum that's unique, and it occurs right here where the derivative of this function is equal to 0. So we can just take the derivative of this thing and set it equal to 0. We get 2ax plus b is equal to 0. We solve for x, and we get that x is equal to negative b over 2a. And sure enough, if you go plot this for yourself or whatever, you will find that for any quadratic that is pointing up, the smallest value that that quadratic takes on is going to be the one located at negative b over 2a. Hopefully this is something people have all seen before in one form or another. Is this trick of taking the derivative and setting it equal to 0 going to work all the time? Yeah. What do you mean? So do we need, right, so what we've done here is what's called the first order optimality condition, and it basically says I know that where this function is minimized, the derivative is equal to 0. And the only place for this particular function we're looking at, the only place the derivative is equal to 0 is where that function is minimized. So we just need to do this, and we don't need to look at second derivatives at all. I'm asking generally. No, right? So you guys probably remember back to when you saw these things the first time. There are various ways in which this can go wrong. It might be that our function doesn't have any minima. It kind of can become arbitrarily small, and it has a maximum instead. That'll happen if this a is negative. This case is not really something that comes up in machine learning because we're going to define our loss functions in such a way that we can't make the loss functions arbitrarily small. Generally, the loss functions can't be less than 0. So that case is not so worrisome, but we can get all kinds of other things that look like this, where we have an inflection point when the derivative becomes 0 somewhere in the middle that's neither a minimum or a maximum. So this trick of setting things equal to 0 is a really useful way of finding closed form solutions if you know ahead of time that your problem has some kind of unique solution that's going to satisfy this condition. That condition is not in general going to hold. But when it does, this is a great way of solving optimization problems. And so, there's an optimization problem associated with linear regression, if you've seen linear regression, that we solve in this way. When we were talking about the maximum likelihood estimator, and we saw that the maximum likelihood estimator was this thing that we obtained by counting various probabilities off of our training set, that actually falls out of a closed form solution that is a little more involved than we have time for today. But something to keep in your head as one sort of general strategy for dealing with optimization problems when they come up. And when we can do this, we really love it because it means we don't really have to do any computation. We kind of know immediately what our answer is, and we can just read it directly off the data set. But, again, this is not so much what happens in the real world. And so most of the time what we're going to be doing instead is something that looks like some kind of local search procedure of a very similar kind to what we saw with CSPs. So to kind of re-ask the question that we were asking again at the very beginning, if I have an objective that looks like this for theta, how is my choice of the loss function going to influence the effectiveness of any local search procedure that I define? And I think it's easiest to see this if we just look at a couple of examples of loss functions. So here's a very natural loss function that we might define. This is sometimes referred to as the 0-1 loss for obvious reasons. This is a function that is going to be 0 when my prediction w dot x is the same as y. And it's going to be 1, I guess here it's actually going to be 2. We should have divided that by 2. It's going to be equal to 1 where my prediction is wrong, right? So kind of these are the only two values I can get. This function is constant in the region where I'm making right predictions. It's constant in the region where I'm making wrong predictions. And then we just have this step at 0. So, this as we've defined it is for a single xy pair under a linear model. What I would like you all to think about for the next 30 seconds or a minute is what this loss surface is going to look like as a function of theta. So basically, if I have two-dimensional theta, I plot it out like this. I'm going to get some kind of surface in 3D that tells me for each value of theta, how big is the loss there on my whole training set. What does that thing look like? Just think about that for a minute, and then we'll actually look. Okay, so let's take a look. What this loss surface is going to look like is this. For how many of you is this what you expected to see? Okay, a small number. So let's kind of unpack. What I did to generate this thing is I generated a bunch of random XY pairs. X1, Y1, X2, Y2. I generated a random weight vector W, which has 2 dimensions. And then I sort of computed this loss function that we've defined here. Okay, so I labeled all of these points. I labeled these Y. Let me start over. I generated a bunch of random X's. I then generated a random weight vector, no subscript. And I labeled all of these X's according to the predictions made by this random weight vector I generated. And these are going to give me my Y stars. 1, 2, 3, like so. And then I said, well, suppose I didn't know this weight vector W here. And I plugged in a bunch of different values for this weight vector. What would this term up at the top look like? So down here, I think corresponds to the region where the real weight vector actually came from. And everything else is what happened if I chose some other value for the weight vector. And so what we can see is that in this region, around the true weight vector, kind of the decision boundary is in the right place, and we're making all of our correct decisions, and so the loss is equal to, well, the loss should be equal to 0, and there's a weird offset here. And as we start to move that weight vector further and further from where we started, the number of mistakes jumps, right? So at this point, we've probably moved the boundary over 1 point. We're now classifying 1 point incorrectly. As we move it farther away, we're going to make more and more mistakes until eventually we get up here, where you wind up with like a negative version of the weight vector, and we're misclassifying absolutely everything. The key thing to notice about this, this loss surface we have is that it looks like a bunch of steps, right? We have these kind of flat regions, and these flat regions are separated by cliffs, essentially. What are the implications of this going to be for any kind of local search algorithm that we try to do on this objective? Yeah?
There's a good chance that whenever it shifts, it doesn't actually gain or lose.
Exactly. So if I'm sitting right here, and I say, well, what would happen if I were to move a little bit in this direction? I would say, well, nothing's going to happen if I move a little bit in this direction. I've made no progress. I'm still making the same number of mistakes. What if I want to move in the opposite direction? Well, if I don't, if I'm just moving a little bit, I've fixed no mistakes. I've made no progress. And so when I'm standing on kind of one of these plateaus, there's nowhere I can see around me that will allow me to actually make progress toward the goal. It can be, we talk a lot in this class about kind of having the right picture in your head, having the right geometric intuition. It can actually be somewhat deceptive when we think about these optimization problems in really high dimensions, right? Because then the number of search directions that you have to consider is not just like up, down, left, and right, but tens of thousands of different ways in which we might be looking. And yeah, and so the key thing here is just that when we have one of these flat surfaces, it's in general going to be very hard to tell which way we should move. And so the picture to have in your head maybe for this, if you're thinking of yourself as an optimizer, is that you're standing on a hillside in very, very dense fog where you can kind of see what the hill's doing right underneath your feet, but nothing else. And you're going to have to choose what direction to walk just on the basis of that. And especially in very high dimensions, this is something that's really difficult. So what we want to think about now is some way of coming up with a better loss function that's going to still have this property that down at the bottom here, where the right answer is, it's going to be equal to 0 when we're classifying everything correctly, but that's going to allow us to have some notion of partial credit for wrong answers and make progress even when we haven't actually fixed anything. There are a bunch of different ways you can do that. Here is an example of one of them. So this is usually referred to as the hinge loss for what are hopefully obvious reasons. And the key thing that we have done here is it's still 0 whenever we're making a correct prediction, no matter how confident that correct prediction is. So we don't get extra credit for being really, really right. But when we're wrong, there are different degrees to which we can be wrong. And if I make a sort of wrong prediction, but this dot product here is very close to 0, that's less bad from my perspective than making a really, really confident wrong prediction when the loss function is going to be some really big quantity over here. So let's do this again. Think about what the loss surface is going to look like for this loss function that we've defined here. All right, we ready for it? It looks like this. And so how many people, this is what they were expecting to see? Okay, very good. Yeah, so, and the key thing to notice here, right, is that there are no step areas anymore, except right down at the very bottom for the set of classifiers that are making exactly correct decisions. And everywhere else, we kind of can't read off of this now directly how wrong we are, but we always know what direction we should move in order to make our predictions better. So that's the hinge loss, and it'll sort of allow us to accomplish the same goal, but it's going to be more friendly to local search procedures in a way that we're going to see in a minute. I just want to throw up one more example of a loss function that gets used in practice a lot, and this is now something that involves probabilities. So, when we said we're going to derive for the naive Bayes model, or we're going to show you for the naive Bayes model, the maximum likelihood estimator, well, we can sort of do a bunch of math and compute that exactly by hand, but we can also do something that looks like this. So for naive Bayes, it's actually, remember, the joint probability of P of X and Y. We could just as easily say, you know what, I don't really care about modeling the density. What I really want to do is just get all of my predictions, all my Ys assigned the highest probability possible. And the way to get these Ys assigned the largest probability possible is to minimize the negative probability, or for numerical reasons, the negative log probability. So that's something that looks like this. And it's going to have the same property as this hinge loss, that it's going to reward partial credit, right? Because now I have to I can't just say what's the Y that I think is right. I have to say for all Ys, what's the probability that that Y is the right one, and the more probability I put on the right Y, the better this is going to be. And if I ever put 0 probability on the wrong Y, or on the right Y, then this will go to negative infinity, and that'll be really bad. This will go to positive infinity, and that'll be really bad. So yeah, so that's the log loss. We're not going to talk about it too much, but it is something that comes up a lot in the context of probabilistic models like Bayes nets, rather than linear boundaries like the ones we've been looking at here. So to kind of take a step back from all of this, we said the second strategy that we were looking at generally was some kind of local search procedure. And when we were trying to motivate local search procedures with these little pictures of these objective surfaces, what we said is we really want the surface to kind of point towards the right answer all the time, right? I want it to be the case that I can walk down the hill and be making progress towards the goal, towards the best possible assignment to the weight vector. And as soon as we're talking about kind of making infinitesimal changes in our parameter vector and expecting that to be reflected in our loss function, now we're talking about derivatives and more generally about gradients. So the key here is really, in formal terms, that we want to design our loss functions in such a way that the gradient is helpful, and then the gradient, which we remember just tells us the direction of steepest descent, is the way we're going to do local search, and is the direction we're going to update our parameters at every step. So just to show this one more time, this rule of following the gradient is not going to work here because the gradient is 0 almost everywhere, but it is going to work over here when the gradient is sort of providing useful information about progress toward the goal. Questions about the setup here? Yeah?
So is the gradient a function, or what is the gradient?
Yeah, so the gradient, right, we had f of x, which is a function from x to the actual amount of the loss, right? What we have now, the gradient of f is a function of x. Sorry, this is the gradient of f of x. This is a function of x that tells you, you can think of it as it tells you the direction of steepest descent along the loss function. From where you currently are. And that's going to be different in different places, right? When you've solved the problem, it's going to be 0, because there's no more progress to be made. When you're way up here, it's going to be really big, and it's going to be pointing, let's use a color that's actually visible. It's going to be, that's not a color that's actually visible. It's going to be pointing in this direction, down the hill. And so, yeah, and a key thing to remember here, and this is going to come up again, the output of this thing is a scalar. The output of this thing is a vector that's the same size as x, because it has to tell me what direction to move all of the coordinates of x. Other questions? Yeah?
I'm just not sure I understand how it knows to point in the right direction.
Okay, so this is the loss function, right? And functions have, we can do calculus on functions, and it, is a kind of fundamental property of the gradient that it points in the direction of steepest descent. And yeah, so this is just something that we know from calculus before. And so there is a quantity that we can compute using f that will tell us that direction. Yeah?
Isn't the hinge loss technically not differentiable?
That is a great question. Isn't the hinge loss technically not differentiable? That is true because right here, the derivative is not defined. This is a little more technical than we're really going to do here, but most of the algorithms that we're going to talk about today are what are called subgradient algorithms, which means you don't actually have to give them the real gradient. It is sufficient to plug in any direction that, where we have corners like this, we can plug in any direction that lies kind of underneath this curve, and they'll still give us the same kind of theoretical guarantees. So yeah, the formal answer is that there are good reasons to expect that as long as we that in fact we can either pick this direction or we can pick this direction at that corner point, and everything will be okay. And then the other thing is just that, like, in practice, right? What are the odds that I actually manage to land right on top of this point where the gradient is not defined? They're very small. The gradient's defined almost everywhere, and so everything will be okay. But that's a good point. Other questions? Okay, so let's look at an algorithm. And this is kind of the obvious algorithm that's suggested by everything that we've said so far. It is called gradient descent. And the way gradient descent works, it looks a lot like the perceptron algorithm, right? We're going to start with our current weight vector. We're going to update our current weight vector in the direction of the gradient of this loss function, which we're calling g on this slide, evaluated at w, at the current setting of that weight vector, and we're going to take a step of size alpha. Why is the sign of this thing negative? Right, because we're minimizing. So if our function looks like this, we're sitting here, this function is increasing, the gradient is positive, and we want to walk in the opposite direction. So that's why we have a negative sign. Yeah?
So how small? Well, I feel like it's kind of hard for W to reach close to zero.
It's kind of hard for W to reach close to 0. So do we want W to be close to 0? We want G of W to be close to 0.
It's hard for G of yeah.
Why?
They get smaller and smaller.
Sorry? Okay, so other people are nodding, so this seems like a question that would be helpful to answer. The question is just, are we never going to, if I have a function that looks like this and I'm taking steps of sort of fixed sizes, how do I know I'm ever going to land right at the lowest point rather than kind of bouncing around close to it? The kinds of guarantees that you actually get out of these algorithms are of the form, if you run for long enough and if you take steps of the appropriate sizes, then after some fixed amount of time, you will probably be within some distance of 0, and you don't get guarantees that you're going to land right on top of the 0. But we don't really care about that, right? Because either we're going to have problems like we were seeing before, where there's some whole big basin of zeros that might be okay, right, corresponding to like the set of all of the linear classifiers that get perfect accuracy on this data set, or we're going to have loss functions that kind of are not going to have exactly that property, but that are going to be good enough when we're close enough to 0. Essentially, yeah. 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 This one. Yeah. So this is just saying for some kind of generic choice of this function g here, which is going to be our loss, which maybe looks like this. We're going to start out here. This gradient descent algorithm is going to tell us how far to step, and
Is it like a rate descent or?
So this is just the loss function.
Oh, the loss.
Right. But the gradient of this function is going to look like, let's use a different color. It's going to look like this when I'm right here. It's going to look like this when I'm right here, and so on. And so these things are telling me how far I should move. Yeah.
Does it make sense, like, so in Q-learning we made a
Mhm.
Does that make sense in this case as well?
Yes, and we're going to come back to that in a minute. Yeah, so, and as in Q-learning, the choice of this alpha parameter turns out to be really important. So here's an example of another problem. This is a slightly different visualization, so now imagine we're kind of looking from the top down at some kind of bowl-shaped thing that looks like this along one axis and looks like this along the other axis, right? So it's long and narrow. We're starting where this red point is. We want to get to the smiley face. What's the direction of steepest descent from this point? Is it sort of more across the bowl, or is it more to the side of the bowl? Who thinks it's across the bowl? Who thinks it's, okay, yeah, I guess across and to the side are not well defined. Who thinks it's this direction is the steepest direction? Okay, who thinks this direction is the steepest direction? A lot of people didn't raise their hands. So yeah, sure enough, this is the right direction. If you know how to read topographic maps, it's the same principle, right? The more lines you're crossing as you move forward, the faster the function is changing. And so this algorithm, in fact, when we're standing at this point, if we make alpha really big, our first step might look like this. It'll take us from here all the way over here, all the way to the other side. And then as we take another step, it'll take us here all the way back to the other side. And so because we made the step size really big, we're bouncing back and forth across. And we're making a little bit of progress because the gradient does point a little bit in this direction, but it mostly points in the direction across the bowl. And so we're doing a lot of bouncing across and only very slowly converging toward the middle. What would have happened if I had made the step size smaller? Yeah, exactly. We might have wound up, let's draw it on top of here. We'd step a little bit in this direction, and then now the steepest way down, and now the steepest way down looks like this. And so we might have converged faster. And so choosing the step size is something that's going to turn out to be really important. We're going to come back to step sizes again toward the end of this lecture. Okay, so that's sort of gradient descent at a very high level. It turns out that this sort of simple gradient descent algorithm that we've drawn here comes in a bunch of different flavors. There are 3 flavors that we're going to talk about today. And the first of these is what's called batch gradient descent. And batch gradient descent is kind of the natural thing that's motivated by all the complaints that we had about the perceptron algorithm so far. And what they say is, before I ever take any step, I'm going to compute this gradient on the whole data set. Right, and kind of by the linearity of this operation, it's equivalent for me to put this gradient inside the sum rather than out in front of the sum. So I'm going to compute gradients for every single training point in my data set. I'm going to add them all together or average them all together or whatever, and then I'm going to take a step in that direction. And if alpha is small enough, what's really nice about this is that we know we're making progress on this global objective, right? We don't have this property anymore that I might have fixed a mistake on one data point but done a bunch of damage everywhere else because we've kind of chosen the direction that's going to be the most helpful for the whole data set overall. Can people think of any disadvantages of this? Yeah.
If you have like a large data set, it would take a while to do this every single step.
Yeah, exactly. And kind of more concretely, if I have a really large data set and all the points are pretty close together, right, the kind of, all these gradients are basically going to point in the same direction. Let's use a different color for the gradients. Are going to point in pretty much the same direction from all of these points. And so it might be the case that if, I kind of just looked at this one, and I moved in the direction that was telling me to move, I would have improved on everything else, but I've done that by only looking at one of my examples rather than having to look at the whole set of examples. And for a lot of real-world problems, this prediction function is something that's pretty expensive to compute, and so we want to do it as little as possible, and we want to kind of get as much bang for our buck as we can. And so this is a reason not to compute this gradient on the whole training set. And so one kind of extreme alternative that we could do is instead to only compute this gradient on a single example. This is called stochastic gradient descent, and that ties into a bunch of other things, but kind of comes from a model in which you are selecting the particular example to make progress on at random. This looks a lot like the perceptron algorithm, right? The only difference is rather than just taking a step in the direction of xi, we're taking a step for our single training example in the direction of the loss of the prediction that we made. Something for you to think about when you go home is whether there is something we can plug in here that will give us the perceptron algorithm back exactly. Is there something that we can plug in for our loss function here, or for some combination of the loss and the prediction that will cause this version of SGD to be the perceptron algorithm? Exactly. Yeah.
So we have to integrate all the data set in this case.
Yeah. Yeah, so we're still using all of our data. The difference was before we would look at all of the data before taking a single step, and now every time I look at a single data point, I'm immediately going to take a step right after that. And so this is nice because it's going to allow us to sort of move quickly on our objective. It's not so nice because of the reason we were talking about before. If I look at one kind of example that's misclassified or in other ways weird, the direction it's telling me to move might not be a good direction everywhere else. And so what people actually wind up doing in practice for a lot of real-world tasks is a sort of compromised version of these two things. This is called mini-batch gradient descent, or sometimes stochastic gradient descent with mini-batches. And as the name suggests, we're going to do something that looks like batch gradient descent, but rather than using the whole data set, we're just going to sort of choose a random, relatively small set of examples that we've called R here. We're just going to iterate over those. We're going to compute the gradient on all of them, and then we're going to take a step in that direction. And so kind of like batch gradient descent, this has this kind of noise reduction property where we're moving in a direction that we know is good on a lot of examples, but we also don't have to compute this gradient on the whole data set before we try to take even a single step. So yeah, you can either do this just by totally resampling these at random on every step. I think what people actually wind up doing most of the time is you shuffle your data, you iterate it over it in chunks of like 100 or 500. When you get to the end, you shuffle everything and then you start over. So that guarantees that you're seeing all the data points the same amount, but you still get a little bit of randomness in there. So to summarize, these are the three flavors that gradient descent comes in. We have batch gradient descent, where we're doing this update on the whole data set. We have stochastic gradient descent, where we're doing it on a single example. And we have mini-batch, where we're doing it on a few examples at a time. And kind of normal sizes for R are somewhere between 100 and 1,000. Yeah?
So could there be more than one local minimum for the loss function?
Yes, absolutely. We're going to come to that in a minute.
So which means by gradient descent, if we find a local minimum, then we get all of it.
Yes, we'll come back to that. Other questions? Yeah. Okay, let's not talk about local minima. We're going to talk about local minima in a minute. Questions not about local minima? Yeah.
It seems that now we're trying to update the weight, but earlier we were talking about optimizing states, or optimizing for the least amount of states.
Okay, so there are two things here. There's like, what's the quantity that I'm trying to minimize, and what's the variable that I'm moving around as I try to minimize it. The quantity that we're trying to minimize is the number of mistakes, or more generally, this loss function we've defined, which is some kind of surrogate for that. The thing that I'm optimizing, so I guess the language can get a little bit confusing because we talk about both optimizing the loss and optimizing the parameters. When we say we're optimizing the loss, we mean we want to make the loss small. When we say we're optimizing the parameters, we say we want to like choose parameters that make the loss small.
So then now are we like, is W the parameters?
W is the parameters, right? Yeah, and so the reason we're making these updates to W is because over time, like we saw on the previous slide, if we take steps in this direction, it will cause this bracketed quantity here to grow small. And that's what we want. Okay, so we can look now at a couple of different variants on this kind of basic optimization procedure. One natural improvement that turns out to have some nice theoretical properties is to introduce what's called a momentum term. So remember previously we were just we're standing at W right now, we see what direction the gradient points, we're going to take a step in that direction, and we're going to stop, and we're going to reevaluate. What we do in methods with momentum instead is we add an extra variable here, which we've suggestively named v. And we say at every step we're going to update not w directly, but we're going to update v. We're going to keep around a little of what v was at the previous time step, and then we're also going to update v in the direction of the gradient right now. And then we're going to update w according to v. Why have we called this thing v? Well, it's kind of like a velocity, right? And so what this is saying is that, maybe initially I'm not moving. And as I'm standing right here, my velocity is going to increase in proportion to the steepness of the slope of the function where I'm standing. And so over time, if I kind of like build up a lot of momentum, if I evaluate several times, and all of these times are telling me go down the hill in this direction, eventually, even by the time I get to the bottom, I'm going to want to kind of keep moving this way. On this example, that's in fact going to cause us to overshoot. But in general, if I have to move really far in one direction, having a momentum term that looks like this is going to allow me to cover that ground much faster than if I had to do the kind of naive gradient descent procedure over and over again. There are a bunch of different flavors of SGD with momentum. They're all kind of similar, and this is all you really need to know about momentum methods, is that we add this extra term v, and we do updates in terms of v. Yeah? Yeah. Okay, yeah, and that is all there is to say about momentum. Okay, so now let's get to this question of local optima that we were talking about before, right? So when we were looking, we also looked at another optimization problem last class, right? When we were looking at k-means, and there were two questions we asked about k-means. We asked about k-means, is it ever going to converge to anything? And we asked, is it going to converge to the best possible place? And we saw that with k-means, it is going to converge to something, but it might not converge to the best possible place. Let's ask the same questions about this gradient descent procedure that we used here. Sure enough, we can get stuck in local optima, right? Because I'm following the gradient, if I start out at this point right here, gradient's telling me I should be moving in this direction, so we're going to update here, update here, update here. Maybe we come up a bit and then we come down. But eventually we're going to settle in probably to the bottom of this bowl right here. This is not a global minimizer of our function. And basically, once I wind up in the wrong basin of attraction, unless I'm doing something like momentum that's going to allow me to kind of break out of that, I'm eventually just going to settle down in here, and there will be no getting out ever again. How are we going to solve this problem? Well, there was a suggestion from somewhere over here before. What was the suggestion? Exactly. So what we're going to do is random restarts. This is something that works. It's like really stupid, but it works surprisingly well for a lot of optimization problems where, if I find that I'm getting stuck in local optima, or I find kind of generally that I'm not satisfied with the quality of the solutions that I'm getting out of my optimization procedure, we just restart a bunch of times, and we hope that eventually one of those times we'll wind up in the right basin of attraction, and that'll get us to where we're going. Just as a kind of historical comment, it was the case for a long time, that people were really afraid of local optima. And rather than kind of writing down the model classes that they really wanted and the loss functions they really wanted, they would carefully design the models and the loss functions such that they had global optima, and you didn't have to worry about getting stuck in these local positions. What we have discovered as time has gone on is that this random restarts thing works really well, and for lots of model classes like neural networks, which we're going to see tomorrow, which have many, many, many local optima, nothing but local optima, essentially, that you could expect to find, all of those local optima turn out to be good enough relative to the global optimum that it's okay to just do this and not worry so much. So the kind of lesson of modern machine learning is don't be afraid of local optima, because sometimes they're not so bad, and when they are, we can often find better ones. Okay, so that's the question of whether or not, if we converge, we're going to converge to the best possible answer. The other question that we saw was whether we're going to converge at all. If we are doing step sizes, if we have a fixed step size like we were talking about before, the answer to that question is no. And here's an example of what might go wrong. I'm sitting right here. I've chosen alpha, the gradient's pointing in this direction, right? So I've chosen alpha in such a way that it's going to send me all the way over here, and here's my new point for this function. Well, what's the gradient telling me to do at this point? It says go back in the opposite direction. The step size is the same. We're going to wind up right back where we started. And so if we keep doing this over and over again, we're just going to bounce back and forth between these 2 points and never actually get any closer to the bottom of the bowl here. What you need to prove kind of theoretical guarantees about the convergence of these, well, so in general, we might not be able to prove theoretical guarantees about the convergence of these things. When we do, we generally have to do it by assuming that we can decrease this step size over time. And so you might have some kind of like 1 over t fall off, where this is getting smaller and smaller like this as time gets bigger. We can do things that look like e to the negative t. We see one thing that people do sometimes is you say, I know I'm only going to run, I'm willing to run for 100,000 iterations. My initial step size is going to be 1. My final step size is going to be 0.001, and I'm just going to linearly interpolate between those 2 step sizes over time. The last thing that people do that turns out to be surprisingly effective is you say, I'm going to set my initial step size to be 0.1. I'm going to run for a long time with that step size until I see that I'm no longer making progress on the objective and I'm just kind of bouncing around. Then I'll drop the step size by a factor of 2 or by a factor of 10, and then I'll keep doing that until it looks like it's gotten stuck again, and then I'll drop the step size down again, and so on and so forth. And just empirically, that seems to be a thing that works pretty well for choosing step size. But yeah, so like we were saying before, it is useful to have this decrease over time. Yeah?
So we're not getting closer and closer to the minimum point.
Yeah.
The shape should be smaller as well because the gradient is smaller.
Yeah. But, like we saw here, it might be the case that I can get, if I have the wrong step size, I can wind up in another part of the function where the gradient is just as big. And that was the example we saw from the previous slide, right? So unless you're also scaling that down yourself, there's no promise that the function is going to help you out in that way. And right, even for kind of reasonably well-behaved functions like this, in fact, the gradient is constant everywhere, or of constant magnitude everywhere, right? So that's never going to decrease as we get closer to the goal unless we do it ourselves. Yeah?
Because it's continuous, I feel like it's going to be really hard to find the exact point where it is 0. So I feel like it would keep bouncing around even if you decrease some.
Okay, sorry, that's not where I was expecting you to go. Yeah, like we said, so right, in the limit where alpha is equal to 0, you're going to stop. And different things will happen depending on the rate at which you approach 0. There's lots and lots of theory that you can do about exactly the right way to do this and exactly the right way to set up your momentum and all that. And if you're interested in these things, take an optimization class, because there are whole classes just on these questions. Okay. Any more questions? So yeah, just to sort of continue our tour of different variants on optimization procedures that we can use, here is something else you can do. It's called Newton's method. You might have seen it in your calculus class before. And it says, we've gotten a lot of mileage out of using the gradient. So let's go to second derivatives as well and do those. What is that going to look like in this case? Well, we have our alpha term from before. We have our gradient term from before. And now we're introducing a new term that involves the second derivative. I think we all kind of know what this looks like for calculus of a single variable. What does this object look like when W is a vector, when our inputs are vectors? And the way we've written it down is hopefully suggestive. It's a matrix, right? And in particular, it's going to be a matrix whose entries look like this. This is, the partial derivative of, we called it G, with respect to x1 and x1 here, and partial G over partial x1, partial x2, partial G over partial x1, x3, and similarly down here, x2, x2, like this. Sorry, no. So I should say basically everything we're going to do for the rest of class today is just to expose you to things that people do so that you recognize them when you come before. You don't have to memorize any of this. It will not be on the exam from here on out. No, sorry. In today's lecture, the next set of slides, we will not evaluate you on. Yeah, starting on this slide. Everything else I think is fair game. Yeah, but so without worrying about exactly the form is, what we mean when we say sort of take the gradient twice is what we're going to, we're going to wind up with some kind of matrix-shaped thing that looks like this. And what Newton's method tells us to do is to take that matrix and multiply its inverse by the gradient that we had before. Why is this a reasonable thing to do? Well, what happens if we have a quadratic function? So let's go back to this example we were looking at before, something of the form ax squared plus bx plus c. So we're going to call this g of x is this. We're currently sitting at a point w, and I want to figure out what my new w is going to be. Well, Newton's method says this is the old w minus alpha, which we'll just take to be 1 here, minus what? The first derivative of this thing, which is 2ax plus b, over the second derivative of this thing, which is 2a, right? And so, yeah, oh, sorry, and this x is a w, because we're calling that variable w. So if I work this all out, I'm going to find that my next w is equal to negative b over 2a, right? This is just arithmetic, and this is what we saw way back at the beginning of the lecture was always going to be the optimum for quadratics. So the nice thing about this is that if we are using Newton's method will, in a single step, take us to the global optimum when the actual objective function that we're trying to minimize is a quadratic. And so what you can kind of think of this as doing is forming a local quadratic approximation to the function that you're trying to minimize, and then going directly to the minimum of that local approximation. And so this is something that, that will perform really well in practice on a lot of tasks. We don't actually ever use Newton's method in this form for real machine learning tasks. Why? Go back to the previous slide. Mm-hmm.
In general, it's pretty expensive to compute the second matrix.
Exactly. So yeah, this matrix of second derivatives, which is called the Hessian, right? If I have 10,000 features or 100,000 features, this matrix is 100,000 by 100,000, and we can barely fit it in memory, much less compute all of the entries one by one. And so what people wind up doing in practice are what are called quasi-Newton methods instead, that form a kind of simple approximation to that matrix on the fly. The most common of these is called LBFGS, and that's what people actually use when we care about getting kind of quasi-second order information. Okay, the last sort of flavor of optimization problem that I want to talk about here is constrained optimization. So far when we've been looking at things in this class, today, we've just said, here's our objective function f, minimize it. But problems that come up a lot in practice, and we've seen some in this class, are constrained optimization problems, where I want to minimize something, and often the thing that I'm trying to minimize is actually fairly simple, and all the structure and interesting stuff about the problem lives in a set of constraints. So I want to find, in Mira, the w that's closest to my old w prime, subject to the constraint that I actually fix the mistake on the current example I'm looking at right now. If you remember, we talked very briefly about support vector machines. There, I want to find the smallest possible w subject to the constraint that it fixes all of my mistakes. And so, kind of in pictures again, it's not enough for us to just optimize this function in a global sense, because the global optimum is here, but we've kind of walled off this whole blue region. And the constrained optimum of this function actually lives over here. Again, there's a whole huge literature on various ways of doing this. One thing that works remarkably well is something that looks like this. This is called projected subgradient, where I compute w prime, which is the update that I would have made if I were doing this like I did before in ordinary gradient descent. But w prime, maybe I'm here, I compute my update, and it sends me right here. This is now outside the feasible region. It's outside the set of w's that I'm willing to consider. So having done this, I just project this one that I computed back into the feasible set. And that's what we're doing here. You wind up with a kind of mini optimization problem inside your big optimization problem. This is often something that's really easy to compute. And so this is a way of kind of dealing with constraints of this form. And again, there are lots of other things that people do, but this is really simple and it tends to work. Yeah?
Could this sometimes lock you out of your optimal solution?
Okay, what are you thinking of?
Well, just for example, for here, the minimum is outside of your feasible zone.
Okay, but so when we talk about the minimum, now we just mean what's the minimum, what is the smallest value that I can get subject to the constraints. So this is the answer we want that we've drawn in the blue box. You can run into other kinds of problems that are similar to the local optimum problems that we were having before, where suppose, for example, my function looks like this, and I want to exclude things in this range. And I initialize here. My function has no local minima. But because I have this like weird constraint set sitting in the middle of it, you know, I'm going to walk down, I'm going to walk down, I'm going to find myself here, and the nearest projection is going to be back up the hill. So I might never be able to kind of break through this barrier and get down to what is in fact the global minimum. Okay, so we've seen a lot about a lot of different kinds of optimization today. If you take away nothing else from this class, or from this lecture at least, this is basically what to remember. When we have small data sets and small numbers of features, and that can still be you know, thousands or tens of thousands of examples, tens of thousands of features, often what we wind up doing is one of these sort of quasi-second order methods, like we were looking at with Newton. And when we have really big data sets and tons of features, like we see in all of these sort of neural nets for vision tasks, and we're going to be looking at that a lot tomorrow, often what people do is just some kind of mini-batch SGD with some kind of momentum thrown into it. And, you know, people play around a lot with different optimization algorithms, but in general, these are pretty good recipes. Questions about optimization? Okay, great. So we have like 10 minutes left in class. I think this is enough time. If not, we'll start it later on. I wanted to talk to you guys really quickly about a project that I did with a colleague of mine a little while back that kind of ties together a bunch of different stuff that we've done in this class. And the project here is automated music transcription. So we're going to get in some kind of audio waveform, whether that's like a wave file or a signal that's coming to us from a microphone or whatever. In this case, we're going to be specifically interested in reconstructing piano music. And what we want to get out is some kind of symbolic representation of the music that's being played, whether that's sheet music or you know, a MIDI file, if you know what a MIDI file is, that just says kind of in time what note's being played, how loud was it, and how long was it held for. And so this is music transcription. You can kind of think of this as like an inverse synthesizer, right? Where I have the sound and I want to figure out what buttons I had to press to make that sound. It turns out, you know, this seems like a really big, scary signal processing problem. We can solve it with Bayes nets. So what you can do for this music transcription thing is actually write down a big probabilistic generative model, a Bayes net, that's essentially a model of a piano. And it works in the following way. We're going to have basically 7 different kinds of random variables in this model. On the right-hand side here, we have variables relating to the music. So this thing up at the top that we've called M is basically the thing that we're trying to reconstruct. This is going to tell me for every note and at every time step, was that note being played or not? And if it was being played, how loud was it? And so the sort of thing that we reconstruct is going to be something that looks like this, copied for all of the notes on the piano. Conditioned on this, I'm going to be able to define a probability of a sort of particular profile of loudness, which is if I had some way of measuring just the amplitude of the signal coming out of the piano as a function of time, what would it look like? And we know kind of on pitch percussion instruments generally, we hit them, there's an attack phase, it becomes loud, and then it falls off. And on a piano, when I lift the key up, that cuts the sound off. Once I know how loud the note is being played, and I know what, in general, that key sounds like when I press that key on the piano, now I can produce a spectrogram, which is basically a kind of representation of the waveform that's coming out of the piano. And so I'm going to have one of these spectrograms for every key. And then what I actually hear at the end is all of these spectrograms added together. Yeah, and so what we have, you know, is a big Bayes net where kind of each of these probability distributions here makes independence assumptions and factors in the ways that we've seen before. Do people have a general, I'm moving fast because we don't have a ton of time and I want to get to the actual demo. Do people have a general picture of what this model is doing? Okay, so we're kind of copying these things that we've drawn here over keys and also over time. And so the inference problem that we have is, can we figure out what the values were kind of parameterizing these things? So, how is this piano played? How often does this note in general get pressed? What is the volume? What is the shape of the change in the volume over time after I press the key? What does it actually sound like on this particular piano when I press that key? And all I get to start with is this final audio waveform with nothing else observed. What are we going to do? Bayes-net inference, right? Just of the kind that we've seen before. Almost of the kind that we've seen before. It turns out, I guess I won't use the whiteboard. We can just do it on top of this. Basically what we're going to do here is something that looks a lot like the k-means procedure where we were doing before, where we say, I'm going to start by fixing all of the things in here to some kind of sensible initial values, maybe random values, maybe kind of sounds that I've heard from other pianos that I can plug in at the level of spectral params. And then I'm going to walk through here and I'm going to say, for every one of these variables, suppose I fix everything around it in this kind of blanket that we get from deseparation. What would be the highest probability value that I could assign to this variable here? So it turns out, well, let's look at this concretely. For these node events here, first of all, what things do I need to condition on to make these node events independent of everything else in this Bayes-net that we've drawn? You guys remember deseparation? Somebody help me out or we're not going to get to the demo. Yeah. Okay, so we're going to condition on this. We're going to condition on this. And also this, right? Yeah, sorry. I've scribbled all over this. It's hard to see. Right, so if, suppose I knew sort of what these loudnesses were, the envelope params, the event parameters, I can then reconstruct the node events. Fun fact, the sort of inference procedure that you do for this is exactly the HMM question that was on the last midterm. So this is actually something that people do in practice. It's called a hidden semi-Markov model, and it's how we do this step of the inference. Without getting into too much detail, there are going to be similar things that happen at all of the other steps. So we're doing something overall that looks kind of like k-means, where we're fixing everything else. We're doing Bayes-net inference over the remaining variable to find a value for that variable, and we're just going to iterate this procedure overall. Sometimes, to find the values for the remaining variables, we're doing sort of normal probabilistic things of the kind that we've looked at in class so far, and sometimes we have things that look like optimization problems over continuous values to figure out what the best thing to plug in at that node of the Bayes-net is. Okay, fine. So we do all of this. We're going to learn some kind of model. I really just want to show you what happens. This is like one of these cooking shows where they just pull the pie out of the oven already baked because it takes a really long time to train. But we're going to start with an audio recording. This is a WAV file that sounds like this. Okay, that is Glenn Gould playing Goldberg variations. When we hand that over to our model, here, I'll show you the terminal doing something just to persuade you that that work was done. No, I won't, because I'm no longer signed into the machine that has a GPU that can do this. What we get out at the end is something that looks like this. This is some sort of reasonable piano roll, and probably the best way of persuading you that we actually did what we were trying to do is to take this music and resynthesize it back so that you can hear what went on. And when we do that, if I can figure out how to make GarageBand play, press space. Okay. And so you can hear it's a different piano. Stop. I don't know how to make it stop. Anyway, so this thing that we're looking at here, you guys know basically all of the tools from this class now to figure out how something like this works. It's just a big Bayes net. You run it backwards, you do posterior inference, and you can do sort of cool, complicated, structured things like this without supervision. So yeah, just wanted to like put that up as a motivating example of the kinds of things that we can do using the tools that we're developing in this class. And if you're interested, the paper is online and I can point you to it. Any other questions about what we've done here today? Okay, great. See you tomorrow.